Okay, so let me, we're cranked up here. So, so finally, we finally reached a pivotal moment here. This is our first due date today for assignments. So y'all been working on those. Most people have finished those with pretty good scores. We've got a few people who are still need to do some extra work on those. So you've got between now and 11:59 p.m. Central Standard Time to get those your last answers in there on those first couple of assignments. And then, so don't forget, our next assignment is due Monday. So you're ready for that one. And then it just continues from there, right? Our first quiz will be due a week from today. I posted one new assignment now, so we're now finally past review and into Chapter 2. So that one's ready to go, and we'll be hopefully, well, I'm pretty sure we'll start discussing that today. We've just got a little bit left to finish here from that review part, and then we'll get into this section 2.1. So you'll be ready, I think, to at least start on that one today. So some of the things in there are already familiar to you. To most of you, some things will be a little bit new. It starts off pretty easily, though, I think. Okay, so getting our feet wet in the calculus it won't be too challenging to start with there. I don't think so. I don't think that's a really super hard assignment. And don't forget the review now. So you need to keep working on the review before the first test, right? And that one's a pretty long, though. I think that's how long is that? Is that 40 questions? Yeah, so that one's long. So I tell you what I'm going to do. I'm going to double the currency on that one. So I'll give you $10 for that one instead of just the regular $5. Okay. So if you divide that by 3, that would give you 3 1/3 bonus points, for instance, on a midterm test, right? Okay. If you make an 82 on that. If you make an 82 on that assignment. But where it will really benefit you on is not making careless algebra mistakes on your midterm test. And that will give you way more points than those 3 bonus points, okay? Because that's where students often bleed points, on making silly algebra mistakes. They know how to do the problem, but they, halfway through it, they make some computational error. And then, they get really frustrated with themselves and start calling themselves names and stuff, or calling me names, even worse. And so I think that will help you not make those sorts of those sorts of tragic mistakes, right? That cost you points, okay? When you really know what you're doing. All right. So, are there any questions? So, if you've already finished the algebra review with the 82, I've got a few people who've done that already. I'll have to go back and adjust your calculus currency because I gave you 5, but I'll go back and adjust that one. So, so give me time to do that. Are there any questions on these 2 assignments that are due today? So today's kind of an important day because we're going to start talking about Chapter 2, and it's unfortunately the weather is not cooperating, so it's a cold day, so I'm afraid that's hurting attendance. But don't forget, of course, as always, so far at least, the taping has worked, so the lectures are posted. Okay, if you just have to miss a day, you can go back and at least watch the lecture. It's not the same as being in class, but it's maybe better than nothing. And of course, you can always visit John, and John will. He's not going to repeat the lecture for you, but he may help you a little bit on catching up if you miss a day. Okay. All right. So anyway, back to this. Any questions about those problems in particular? So, yeah, most people. So the median score on those is pretty high. So most people seem to be getting through it all right, but any things that were causing you issues that you want to ask about? Don't be shy about asking me questions now, okay? All right? Better now than after the test, right? Don't come up and say, oh, I don't know how to do this problem, okay? Better get that solved before the test rather than after you've missed it on the test. One thing about the web assignment I do want to caution you about, so no one's asked about this yet, but this is going to come up, is, these are a couple of examples that we're going to do today. In this book especially, in a lot of the formulas, there are lots of decimal places, okay? So, and you can see it in these two examples. The coefficients often of terms often have lots of decimal places, sometimes unnecessarily many. I created this example, so I think I got a little bit carried away because this one has 5 or 6 decimal places sometimes. All right, but you're going to notice that quite a bit in the homework problems. And when you're asked to enter answers, it will often ask you to enter things to several decimal places, 2 or 3 decimal places, sometimes 3 decimal places, which is a little bit excessive, I think, but that's just the way the problems were coded, okay, by whatever programmer coded those. So pay attention to those instructions when it asks for a certain number of decimal places, because that will count you wrong, all right, or can count you wrong in the homework problems, even if you get everything else right, okay. So sometimes it's rather exacting, okay. All right, so, well, that's good. So I'm hoping that not hearing any questions, that means that everyone feels comfortable with, so far, with what we're doing, okay? And again, it's review, so not unusual not to have that many questions up until now. Last time we were talking about properties of functions, in particular as related to the shapes of their graphs, okay? And so we were talking about the direction of curves, and that means increasing, decreasing, or constant, right? Okay, and how to write down in the standard mathematical accepted way where a curve is increasing and where a curve is decreasing, or where a curve is constant. And today we're going to talk about also a second idea, which is called, which deals with the curvature of the curve, okay? And that is, in mathematics, that curvature is called concavity, okay? So that's kind of a fancy term, but it just means curvature, all right, when we're using that, okay? So we looked at this example last time, and we just wrote down, remember, in interval set notation, right, where this curve was increasing, and where it was decreasing, and where it's constant. It's not, that looks like the answer is constant right there, right? But it's not, this curve is never constant. It's always either increasing or decreasing. It was increasing on 2 intervals, so I combined them using the union operation, right? So when you're looking at that in the notes, don't think it's constant from 2 to infinity. It's actually increasing from negative infinity to negative 2, and then again from 2 to infinity, right? And then it's decreasing from negative 2 to 2. And remember, we always give our answers for where a curve is increasing or decreasing in terms of the x-axis, in terms of the input axis, but the increasing or decreasing actually refers to the outputs, okay? So this curve was decreasing from negative 2 to 2 along the x-axis, but what that means is that the outputs, the y values, right, were going down as the x values increased from negative 2 to 2. So if we move from left to right along the x-axis from negative 2 to 2, right, okay, the output values, the y values, were decreasing. Okay, so that's how that answer came about as to where the curve is decreasing, and then increasing here from negative infinity up to negative 2. Right, okay, and again, that's in terms of the x-axis, right, okay, and then increasing again from 2 to infinity, okay, so from 2 to infinity, the outputs are going up, apparently all the way out to infinity, although we can't see all that curve on the right-hand side, and also increasing over here on the left-hand side as well, right, the y values are going up as the x values increase from negative infinity to negative 2, okay, and these points where the curve switches from increasing to decreasing or vice versa, we call those points turning points, okay, so I refer to those as turning points. So here's a turning point because this curve switched from increasing to decreasing right here, and here's a second turning point because here's where the curve switched from decreasing to increasing. Where a curve switches, remember, and this is kind of a tricky thing, where a curve switches from, say, increasing to constant or constant to decreasing, that's not actually a turning point. Turning point has to be where it switches from increasing to decreasing or vice versa. Okay. All right, so there are the locations of, there are the coordinates. I just estimated them. I hope I estimated them correctly. Yeah, here are the coordinates estimated of these two turning points. So coordinates there of this turning point about -2 on the x-axis and about -0.8 on the y-axis. I was just eyeballing it. And then here, the coordinates of this turning point about 2 on the x-axis, right? And then I was thinking that was about, looks like it could be -3 as well, but I put -2.9 on the y-axis. And that's one of the things we're going to be doing in the class a lot, is writing down coordinates of the turning points. Those turning points are going to be very important points to us in this class. Okay, they play a real key role in calculus because they help us answer lots of important questions, both practical questions and sometimes kind of theoretical questions. So we're going to be finding locations of turning points quite a bit, sometimes just estimating them by looking at a graph like I did here, but actually we'll learn how to actually analytically with pencil and paper find the location of turning points as well, okay, without having to just estimate them from the graph. Okay, all right. So there's a real quick summary there of what's called function direction, increasing, decreasing, or constant. But one other now little piece of terminology I want to introduce to you here that, again, you may have heard this before. If you have a turning point, okay, all right, so here's a peak turning point, right? I call this a peak turning point because notice the graph there sort of forms a hill right there around that turning point, right? A peak turning point is where the curve switches from increasing to decreasing, like this one. All right. So if you have a peak turning point, the y-coordinate of the turning point, that is referred to as a local maximum. Okay. So that value minus 0.8 there, we're going to call that a local maximum. And the reason that's called a maximum is because close to that turning point, right, close to this turning point, this is the maximum output value for this curve. This is the maximum y value for this curve. Close to, now notice I said close to the turning point, okay? Notice when you get over here far to the right, you have much higher output values, right? Okay, so on the far right, your y values can get very large, right? Looks like they're actually shooting all the way up to positive infinity. But close to the turning point, the maximum y value we have on this curve is right there at minus 0.8. So that is referred to as a local maximum. Okay. Now, if you have a valley turning point, the y-coordinate of the valley turning point is referred to as a local minimum. All right? So for a valley turning point, the y-coordinate, the value itself is called a local minimum. And again, what that means is close to the turning point, maybe not on the far right or on the far left, but close to the turning point, your smallest, your minimum y value is going to be, for this curve, your minimum y value is going to be minus 2.9. Okay? Now, all right, here's a little point of confusion. All right? Sometimes a local maximum in many situations, we confuse local maximum with the turning point itself, okay? But actually, that's not correct, okay? The local maximum is the y-coordinate of the turning point. The local minimum is the y-coordinate of the turning point, all right? But sometimes you will see the idea of turning point and local maximum or turning point and local minimum sort of conflated with each other, okay? So some books refer to the point itself as the local minimum, or some books will refer to the peak point itself as the local maximum. But technically that's not correct. Local maximum means or local minimum means the y-coordinate of a turning point. You understand the difference there? Okay. So a turning point is a point. Okay. A point has coordinates, right? Okay. But a local maximum is just a number, all right? Or a local minimum is just a number. It's the y-coordinate of a turning point, all right? Okay. All right, let's look at this example, okay? And what's tricky about this example, so this is where we stopped last time. What's tricky about this example is you've got this complicated formula, and you're going to be asked, okay, for this function, where is it increasing? Where is it decreasing? Okay? And what are the coordinates of the turning points? What are the coordinates of the turning points, if there are any? By the way, you know, curves don't have to have turning points, right? Okay, so this could be a bogus question, all right? But nevertheless, you're just given the formula here, and you're asked questions about sort of, what the graph looks like, right? So to answer this question, and to find the coordinates of the turning points, or to estimate the coordinates of the turning points, what are we going to have to do? We're going to have to make the graph. That's right, okay? We're going to have to make the graph, right? Okay. So we're going to have to take that formula, and we're going to have to convert it to a graph, because at this point, that's the only way we know how to answer these questions, right, is to convert it to a graph. Now, what we're gearing up for, but we have to build the machinery for this first, is how to answer this question without actually making the graph, okay? And when you learn how to do that, that's when you're going to really have learned a substantial amount of calculus, and you'll be a really smart person then, okay? You're gonna know it too, right? You're gonna feel your brain getting larger, okay? I mean that literally, all right? Okay? You know, when you practice things and learn new things, you know what happens, right? The neurons, your brain cells, right? They form new connections, okay? So actually, the mass of your brain actually gets a little bit bigger, okay? It's just like a muscle in your body, okay? You know, when you go and exercise at the gym, like I'm supposed to do tonight, but I hope I don't goof off, okay? You know, you do that long enough, right, your muscles get bigger. Your brain is exactly the same way, okay? So when you start learning this calculus, your brain's going to get a little bit bigger, okay? Maybe not, 5 or 10 pounds, right, okay? But a little bit, all right? Okay. All right, so let's make the graph, okay? Now, if we had to do this by hand, this would really be a really tedious problem, okay? But we're not going to do it by hand, right? So we're going to use the computer to help us make the graph, and that will make the problem much easier. Oh, let's read the problem first, though, so before we actually start making the graph. That would be a good idea. Always a good idea to read the problem first. So this problem says the following function formula, so there's the formula, that big ugly formula, and I wrote it down up here, okay? This can be used to predict the percentage, so it's the output value here is a percentage, okay, of all car injuries resulting from accidents where humans were driving, okay? Now, when you first look at that, you're thinking, isn't that 100% always? Because humans are always driving cars, right? Okay, so all car injuries are caused by accidents where humans are driving. Well, yeah, today that's correct, okay? But of course, what's going to happen in the future, all right? I may not be around to be part of this, but you certainly are. How are cars going to be operated in the future? I see y'all are not really keen on this, all right? They're going to be driverless. That's right. Yeah, okay. So they're going to be computer driven. All right, okay. So that's the vision, right, at any rate, correct? Okay, so when you're ready to go somewhere, you may not actually own a car in the future. When you're ready to go somewhere, you may use your cell phone, right, and an app on your cell phone, right, to actually summon a vehicle, okay? All right. Well, okay, now that was really far in the future, all right, I think, okay, all right, but in the not-too-distant future, at least, right, okay, use your cell phone, right, okay, an app on your cell phone, right, to summon a vehicle, a driverless vehicle, to come and pick you up, right, and take you where you're going, and you'll pay a small fee for that, right, and that would be perhaps even cheaper than owning a car, right, where you have to have monthly car payments and stuff, okay, well, that's sort of the vision of the future. So in the future, you see, okay, it will be the case, right, that when accidents occur, they may happen because in vehicles where, humans were not actually doing the driving, right? So if you look very carefully here at the formula, notice what it's got as the input value here is elapsed years after 2000, and notice the domain of this function is given to us as 23 to 32, okay? So notice this is making a prediction about the future from when? Starting in what? So what year would that be? Yeah, 2023, right? Okay, up to 2032, okay? All right, so so let's graph that curve and see what it looks like, okay? All right, so remember the output is a percent. The input, of course, is elapsed years. We're used to working with elapsed years, so that's not new to us. The output here is not the number of car injuries, but it's the percentage of car injuries, okay, resulting from accidents where humans were still driving, okay? All right, so let's switch now to our web page, right, that we're going to use for doing graphing. I'm going to use a couple of web pages here actually in the class, but this is my favorite one. So this one is called Desmos, remember. So it's www.desmos.com. So it's so easy to use. That's why I like to use it. And so this is what I'm encouraging you to get used to using, all right? If you need to make graphs for your homework, okay? So just go to that web page, all right? There's a link to that right from the WebAssign website, okay? And when you get there, you'll see this. So you have to go to Start Graphing, and it will load this graphing calculator. Now, of course, there are lots of websites, right, and apps that will do graphing for you, so you don't really have to use Desmos. You can use something else if you want to. If you have a graphing calculator, you can use your graphing calculator as well. That's fine with me, all right? So whatever technology you're comfortable with, but pick something that you can use, right, because we're all going to have to occasionally here construct graphs, all right? All right, so let's see if we can type in that ugly formula now, and so this is where this is the only messy part here, really, of using Desmos is typing in the formula. So y'all got to help me here type in these coefficients. So what is it? Minus what? Point. I'm going to skip the first 0 there. So y'all read that off to me. 0 what? Go ahead. 5.2. 1.5. 0.5. Is that it? Yeah, x cubed, right? And so remember, to get the x cubed in Desmos, just type the x, of course, and then to get the exponent, you have to use the caret key, which is the shift of the 6 key, right? Okay, and then you can use the right arrow to get out of the exponent, all right? So, and remember, Desmos now is going to graph dynamically, so as you're entering the terms, it'll start graphing it. So this is not the graph that we're going to look at, right? Okay, that's just the graph of the minus 0.521.505 cubed, okay? But we've got these other terms that we have to add on, so let's put those in. So let's see, now plus there and what? Okay, read that one off to me. I got a couple of them. 4.89 what? 168. Is that it? Okay. Yeah, x squared. All right. All right, so again, just hit the caret key there. Okay. And then minus 150 point, what is it there? 145. X, okay, and then finally the constant at the end there, not so bad, 1601.5. Is that right? Ah, okay. All right. So there it is, and as usual, right? We look at that, and darn it, we don't see anything, right? Okay. So we get frustrated, but we got to look at where we're positioned here on the x-axis. Because remember, what did this say about the domain? Yeah, it's 23 to 32, right? So I've got to move if I'm hoping to see something here, of course I could have typed in something wrong, right? I've got to move my x axis over here, right, to 23 to 32, correct? Okay, and then remember this is a percentage, so let's look up there and see if we can see that. There, finally. See, I almost gave up. Okay. Right. But there it is. And you can, well, that's good enough, I think. All right. Okay. Because, let's see, we're seeing 23 to 32, right? Okay. So we've got the domain in here that we can look at. And you know this is a percentage, right? So we really don't have to worry about a percentage bigger than 100, correct? So even if we see the curve there extending above 100 on the y-axis, we know that's not a valid part of the curve, right? Okay, because you can't have a percentage more than 100%. All right. So I think I can use this piece of the curve, right, to answer the question. So what is that curve telling me before we actually answer the question that's asked? What's that curve telling me about this situation? Well, right now, right, right now and in 2023, how many of those injuries are going to result from accidents where humans were driving? It's 100%, right? Okay, right. So that makes sense, right? So probably that tells us in 2023, we're probably not going to have that many driverless cars still, right? Okay, yeah, so still in 2023, it's still going to be mostly humans driving cars, okay? So that makes you feel a little bit better for the next 8 years or so, right? Or 7 years, right? People still going to be mostly the people driving cars. But then what happens? Yeah, see, that percentage begins to fall, okay? So as we get more and more of these driverless cars on the road, right, then the percentage of injuries caused by humans is going to go down, you see, okay, right, okay, because there'll just be more and more of those driverless cars, correct, okay, so they'll be involved in more accidents, right, and down to here. But then notice past about 2026, at least according to this prediction, notice an interesting thing starts to happen, okay, an interesting thing starts to happen. Notice the percentage goes up again. So what's that telling us about up to about, well, what does it start? End at 2032. What's that really telling us there about the future? Is that saying that we're going to abandon driverless cars and humans are going to start being the ones driving again? Is that really what that's telling us? No, I think what that really is telling us is the driverless cars are going to start getting really good, okay? And they're not going to be involved in accidents, all right? Okay? So the computer technology is going to be getting really good, and those driverless cars are not going to be involved in accidents. Who's going to be causing all the accidents? Yeah, situations where humans are driving, you see. Okay, right? Okay. So the driverless cars won't be involved in accidents because the technology will be very good, right? Okay. So when you do have an accident, right, it's going to probably be because of what type of error? Not a computer error, but what? What? Human error, that's right, okay? So it'll be human error involved, okay? This has led to some speculation. Actually, this curve, this prediction, has led to some interesting speculation. There's some people who think that in the future, humans will be banned from driving, in fact, okay? Humans won't even, in fact, be allowed to drive, okay? Why? Because guess who will be causing all the accidents? Humans, that's right, okay? So if you want to ride somewhere, you won't be able to drive, okay? Because you're just not going to be as dependable as the computer, right? Okay? It'll be the humans causing all of the problems, all right? So interesting there, all right? So anyway, what's the question that we were asked? Let's see if we can Let's go back now. That wasn't the question we were asked. So for what time periods is the percentage decreasing? For what time periods is it increasing? Well, that's easy to see, right? Okay. So where is this percentage? Remember, this is a percentage, right? So where is the percentage decreasing? Starting at where there, Zaman? 23, right? Yeah, so don't go outside of your domain, right? Okay, so decreasing from 23 to what? Looks like about 27, right? Okay, and then increasing again from what? To 32, right? Okay, looks like it's increasing again for the rest of the domain. Be sure you keep your answer now within the domain. Can I squeeze that in there? Let's see. So decreasing from 23 to 27, okay? And remember, usually when we describe where a curve is increasing or decreasing, we just use the open interval, right? Okay? And where is it increasing? From 27 up to what? 32, right? Okay? So increasing from 27 to 32, okay? And to figure out where it was decreasing and where it was increasing, of course, you really had to know where that turning point is. So the next question there is just estimate the coordinates of the turning point. And looking at the graph, that's so easy to do, especially in Desmos, because Desmos actually picks out those turning points for you. So what is it there? Actually, Desmos says it's 27.036. Can you all see that? Okay, I'm going to round that off to 27. And the y-coordinate there, let's round that off to about what? 87, yeah. Okay, so now look, if you're entering this answer in WebAssign, though, and it asks for lots of decimal places, be sure you enter the decimal places, okay? But I'm going to just get lazy here and write 27 and 87 as the coordinates for that turning point, okay? All right, so there's our turning point at, well, I didn't even write that on the board. I can remember that, okay? So the coordinates of the turning point there, 27 and 87. That looks kind of like an interval set, right? But remember, these are actually coordinates of points. That's not coordinates of points. That's actually a set of numbers, all right? And so there is our turning point. And again, what's that 87 called? Local minimum, right. Yeah, that's an example of a local minimum, okay? Because that was a valley turning point, okay? So even if you're just given a formula, right, okay, even if you're just given a formula, you can still answer questions about where the function is increasing or where the function is decreasing, but right now, to do this, we're going to have to make a graph of the formula, right, okay, and give an estimate, all right? So there is our estimate for that turning point. All right, now let's talk about our second sort of property of curves, okay, and similar to direction, but this relates to the curvature of a curve, okay, as opposed to its direction. All right. So we describe the curvature of a wiggly curve, okay, not a straight line, okay, but a curve that has some wiggles in it in two ways, okay. So we say a function defined on an input interval is said to be concave up, all right. So you can think of that concave as the word curved, all right? So curved up, concave up, if the graph appears to be a portion of an arc opening upward, And the opposite is concave down if the graph appears to be a portion of an arc opening downward, okay? So again, concavity, concave just means curved, all right? Let's take a look at a wiggly curve here, and let's see if we can answer where this curve is concave up and where it's concave down. So you give your answer very much like you would increasing, decreasing. You give it always in terms of the x-axis. Okay, let's start with concave up. You give it always in terms of the x-axis. All right, okay. So remember, we're going to write down a set here, but the set is a set of x values. Okay. So concave up means where does this curve appear to be an arc opening upward? Where does it appear to be an arc opening upward? All right. Well, is that the left or the right? Yeah, it's the right, obviously, right? Yeah, this portion of the curve, right? That portion of the curve appears to be a arc opening upward, right? Okay. See, concave up. By the way, if this graph were a straight line, a straight line doesn't have any curvature at all, so it's not concave up or concave down. So concave up or down does not apply to straight lines, right? Only to curves with wiggles in them, like this one, right? So again, obviously, it's this right portion of the curve here that's concave up. Now, the left portion on the curve, though, notice, right, is an arc opening downward. So there's a switch that occurs somewhere from concave down to concave up. And to answer this question, we have to figure out where that switch occurs. Okay, so where on that graph does that switch appear to occur? Well, I'm just going to guess right here. I think it's right there. Y'all agree or disagree? I'm just giving it an eyeball estimate. Okay, does that seem like a reasonable place there? Okay, see, that portion of the curve is an arc opening downward, right? But this portion of the curve is an arc opening up, and the switch occurs, I'm going to say, I think, right there at that point. Does that seem reasonable to you? Okay, as just a guess, all right, an estimate. That point right there, by the way, as you might expect, that has a name, of course, but it's not a turning point. Where are the turning points here? Yeah, the turning point is up there and one down here, right? Okay, so this point is different from a turning point, but that is an important point. That's where the curvature switches. That's called an inflection point. Have y'all heard that term before ever? So right there, where the curvature changes, that's called an inflection point, okay? And just like with turning points, it's going to be important to us in the course to estimate coordinates for inflection points, okay? I'm not going to try to estimate the coordinate for that inflection point, okay? But that's one thing that we're going to be doing in the class, is locating those inflection points and trying to write down where their coordinates are. Okay, so, well, I kind of do need to know what the coordinate there is, though, right? Because I've got to answer this question of where it's concave up, right? So it's concave up starting right here on the x-axis. What is that on the x-axis there? Let's see, this is 1 and this is 1.5. So if you're in the back, you can't see very well, but Zaman said it right. I think it's right there at about 1.75. Okay, so remember, we're just giving an estimate here, so answers may vary slightly, but I think Zaman is saying what I would say, about 1.75. Okay, so it's concave up starting at 1.75, and then apparently continuing, I guess, all the way out to infinity. I'm not really sure, right? Okay, maybe the curve turns over here and changes concavity again somewhere on the far right, but I can't see it. So it looks like that just continues all the way out to infinity. Okay? Is that confusing? It's not quite as obvious as increasing, decreasing. Okay? So what about concave down then? Well, once you've got the concave up part, then the concave down part is pretty easy, right? Okay? Because where's it going to be concave down? Just on the left, right? Okay. All right, so that is starting where? Negative infinity, right? Okay. And apparently up to where that inflection point is on the x-axis, which is right there at 1.75. Okay. At least that's my estimate for it. Okay. But again, I'm just looking at the graph, so my estimate may be off by a little bit. All right. All right, let's try practicing that again, because that may be You've probably seen increasing, decreasing before, but concave up and concave down, that might be new to you. All right. So here's one I've drawn by hand. Oh, this is the same one as before, right? Okay. But we're not asking about where it's increasing, where it's decreasing. Instead, we're asking where it's concave up and where is it concave down. Okay. So see, that's a nice wiggly curve, right? It's not a straight line. So we can answer this question where it's concave up and concave down. If you're given a straight line and you're asked where is it concave up or where is it concave down, you're going to say nowhere, okay? Because concavity does not apply to straight lines. Concavity is about curvature, all right? But this one does have some definite curvature to it, right? Okay, so we can get an estimate here for where it's concave up and where it's concave down. All right, so that's what I want y'all to do. Give me an estimate for that. Where is it concave up? All right, and where is it concave down? And remember, you're going to give your answer in terms of the x-axis. It's set of values on the x-axis. So in a sense, the y values here are kind of irrelevant, okay? Where is it concave up? Where is it concave down? And it may be concave up in multiple places, just like it can be increasing multiple places, and it may be concave down in multiple places. So, you might have to take the union of sets here to answer where it's concave down, or you might have to take the union of sets to answer where it's concave up. Okay, but usually the concavity is not as complicated as the direction. All right, just as a little hint there. Okay, all right. So y'all try that one. Shouldn't take too long. So take a minute there. If you need to come up, if you're in the back and you can't see very well, you're welcome to come up and peer at the graph there. Okay. Compare your answer with your neighbor if you're not confident of your answer. Okay, because I'm going to ask someone to share their answer with us. Okay, or maybe a couple of people to share their answer with us there. So if you're confused there about this concept, ask your partner or your neighbor there. Turn to your, I always call this your shoulder partner, whoever's sitting next to you on the left or right, whoever looks the smartest. Ask them, okay, what the answer is, okay? All right? So if I call on you, you'll get it right. So remember to give your answer in terms of the x-axis, though, not the y value, right? X-axis, x-axis. Right? Yeah. Yeah, something is happening right there at -2, but remember, where is that on the x-axis? Yeah, but what's x? Ah, there you go. Right, yeah. Okay, yeah, okay. Yeah, you just estimate it. It's not really guessing, okay? But it's kind of like guessing, yeah. Okay, but what we're working on, Zaman, is to take the guesswork out of it, right? Okay, that's what calculus helps us to do, all right? But right now, we're just trying to get the concept down. So again, when you're signing the attendance sheet, right, make sure you sign in your usual spot, right? Okay. Okay, y'all think y'all figured that out? The buzz is dying down. Okay, the excitement is gone. All right. So, all right. So let's try. Let's see. Let's compare answers here. Miguel, is Miguel here? Miguel, okay. So let's start with concave up, okay. So where did you think it was concave up?
Would it be 0 to infinity?
Concave, perfect, yeah, okay. I thought you were wrong because I was doing it wrong, yeah. But you're right and I'm wrong, okay. Yeah, concave up means it's a upward shaped arc, right? Okay, yeah. And that is on the right-hand side of this curve, right? Okay, yeah, the right-hand side of this curve is an upward shaped arc. And on the x-axis, that starts at 0, okay, and apparently goes to infinity, okay, as far as we can tell, right? We're not sure, but that's the best we can do with what we're given, all right? So, yeah, exactly right. All right, so Miguel got the hard part, and now Sandy gets the easy part because where is it concave down? Say Sandy here? Yeah, Sandy, okay.
Negative infinity to 0?
Yeah, right, it's just the other side, right, okay. Perfect, okay? So negative infinity to 0. Y'all did that beautifully. And right there, apparently, is the inflection point, okay? So right there is the inflection point, and that's right on the y-axis, right? So here we can get a pretty good estimate for the inflection point, right? It looks like 0 and negative 2, okay? So some people were trying to include the negative 2 in their answer, but remember, that's a y value, right? Okay, and that really doesn't play a role in the answer, okay, of where it's concave up or concave down. That is part of the, if I ask you what are the coordinates of the inflection point, that's part of the answer, but not really part of writing down where it's concave up or where it's concave down, okay? So only one inflection point on this curve. There are usually fewer, you'll learn why this is true a little bit later, but usually there are fewer inflection points than there are turning points, okay? Fewer inflection points than turning points, okay? That doesn't have to be the case, but typically that's the case, okay? So this one has 2 turning points, but only 1 inflection point on it that we can see anyway. All right, let's go back to my driverless car example because I'm fascinated by this, although I'm not sure I'm going to get into a driverless car. I'm just maybe too old for that. All right. So, see, the promise of driverless cars is that there'll be fewer, they're more reliable, and there will be fewer injuries resulting from car accidents, okay? And that's exactly what this graph shows, okay, because this graph, this function can be used to predict the number of injuries. This isn't deaths, but the number of injuries resulting from car accidents in millions. There are lots of injuries resulting from car accidents. There are not that many deaths, but lots of, because this can be minor injuries like, a sore neck or something, right? Resulting from car accidents, X elapsed years after 2000 again. So this has got exactly the same domain as that previous example, okay? The domain begins at 23 on the x-axis and goes up to 32 on the x-axis. And here x is measuring elapsed years. So this is a prediction for 2023 up to 2032. So that's good for you, okay? Well, I'll probably still be alive in 2032, all right? So good for me as well, all right? Unless maybe I die in a car accident before 2023, right? But anyway, good for us all because notice that the number of, the predicted number of injuries from car accidents is declining, you see, all right? So that curve is decreasing over the domain, okay? All right, but here's the question. This is not about increasing, decreasing. The question is, for what time periods is the graph concave up? And for what time periods is it concave down? And we want to, again, estimate the coordinates of the inflection point. So that's definitely a curve, okay? Definitely a curve, not a straight line. So it does have concavity, but this one is maybe not quite so obvious. Maybe it is, okay? But it's a little bit more subtle than the than the previous examples as to where it's concave up and concave down. All right, so give me a shot at that one, okay? Try to write down where it's concave up, where it's concave down, and then we'll try to estimate the coordinates of that inflection point as best we can. But it'll just be an estimate because we're going to be looking at the graph, all right? So try this again. Concave up, concave down, and then where is that, do you think is that inflection point? So if you have to come up here and squint at the graph, feel free to do that. Okay. So this is coordinates for inflection point. So remember, you're going to give me coordinates here. All right. Okay. So try that. So again, compare answers with your friend and your right. Okay. Your shoulder partner. This is our last concavity example. So before your homework, so you got to get it straightened out here, okay? So you'll be able to answer these questions on your homeworks. So do all three parts there for me, okay? Maybe easier to start with the inflection point, actually, because that's where the concavity changes, remember? And so once you've got that sort of located, then you can easily write down where it's concave up and where it's concave down. Notice this curve has the domain does not extend to infinity on the left and the right, though, okay? Stops at 32 on the right and 23 on the left. So incorporate that in your answer. Mm-hmm. You know, that's a good question, but let's try using parentheses. Yeah, I'm tempted to use the brackets too, but let's try to stick with parentheses for increasing, decreasing, and concavity. And then, if the homework is not grading us right, we may have to switch. Okay. That's always a kind of a controversial issue. Even amongst mathematicians, about whether you should use the brackets or not, or use the parentheses. Okay. Okay. All right. Y'all seem very confident of this. That's good. All right. Because this is always. Sometimes this throws people, okay? So, by the way, notice on this curve, no turning points, okay? No turning points because this curve is always decreasing. It looks like if the curve continued over here on the right, it's trying to turn up, right? Okay? But that never quite actually happens in the domain. And same thing, it looks like over here on the left, the curve is trying to turn over and change direction over here on the left, but because the domain is cut off, that never quite happens. So there are no turning points here because this curve is always decreasing. These are not turning points, all right? Look like they're close to being turning points, but they're not quite turning points. All right, but there is an inflection point, okay? There is an inflection point here, kind of subtle. All right, so let's find that first, and then that'll make it easier to answer where it's concave up. So I'm going to ask someone to help me find the inflection point. Is Christian here, Manasco? Okay, Christian. All right, here's what I'm going to do to help you with this. I'm going to just point there at the curve, and I'm going to move from left to right, and you tell me to stop where you think the inflection point is, okay? So I'm moving along the curve, right there? That's your guess right there? So that is right above, can y'all see that? What's that? Right above 26? Okay, all right. So Christian says inflection point right there. What does the class say? Do y'all agree? How many agree with Christian? Raise your hand there. Okay, so so if you don't agree with Christian, raise your hand. So everyone else is, oh, Christian, you're outvoted there. Okay. Oh, you're changing your answer too? You don't agree with yourself? Okay. All right. So why? So how do you want to change your answer, Christian? You don't? Okay. You don't know? Okay. Yeah. This is very subtle. Okay. This is very subtle. So this is open to a little bit of interpretation. I would actually say I think the inflection point is more right about there. Okay. Or maybe even a little bit further, maybe right there. This is one where you really have to, really give it your best, really examine it. It's where the arc changes from being curved down to being curved up. Okay, and I think it's still curved down a little bit to the left to the right of where you said. I think right about there maybe is where the inflection point is. Do y'all understand what I'm saying? Okay. Does the class sort of see what I'm getting at? No? Yeah, I still think kind of an arc all the way, an arc opening downward all the way to about right there, and then it becomes an arc opening upward. You see what I'm saying, Christian, a little bit? Okay. It's very subtle when you're trying to just eyeball this, especially where it's not obvious, okay, where an inflection point is. But I think you got it a little bit too far to the left, okay, a little bit too far to the left. I would like to put it maybe closer to right here, okay. This is one that really takes some practice, okay, to start getting really very accurate on this, okay? And this is where calculus will really help us, because calculus will help us not have to do guesswork on where the inflection point is, but we'll actually be able to determine it exactly, all right, without trying to eyeball it. So let's see, what does it look like the coordinates of that point are that I have picked out? There's 27, so it looks like my x-coordinate is above 27 and a half, all right? Okay, so I'm thinking the x-coordinate there is about 27 and a half. And the y-coordinate, oh boy, that one's even tougher. Looks like, yeah, maybe about 1.1. Okay, a little bit above 1 on the y-axis. By the way, what is that point telling us about the injuries? Well, our prediction is that around 2027, right, the number of injuries would be, 1.1 million, okay, right, which sounds like a lot, but remember, those aren't all deaths. Those are, that could be all sorts of injuries. That could be a broken toe or something, okay, all right, in a vehicle injury, okay. So I think right there, a little bit closer to the inflection point. I still think some curve down up to that point, and then it becomes curved up on this side. All right, so, now, once we've got the inflection point located, though, then this part is easy to answer, okay? So, where is it concave up? Marco, is Marco here? Marco, yeah, okay. So, where is it concave up?
To where it stops, I guess.
Okay, so when you say from there, what do you mean by there? From the inflection point. So help me write down that set. Concave up from what number? 27.5? Yeah. Okay, 27.5. So that's the x-coordinate of the inflection point. And then to where, Marco? What? 32, right. Yeah, first you said, I was hoping you'd make the mistake again, but you caught yourself. Okay, not to infinity, okay, but just to the end of your domain, right, okay, to 32, okay. And now, concave down, okay, so Marco and Christian have done all the hard work, all right. So concave down, Vanessa here? Vanessa, yeah, where is it concave down? So it's got to be what's left, right? This part is already concave up, so that means it's this part that has to be concave down. So what's that part? Starting where? Not negative infinity, okay? where does the curve start at? See, the curve is cut off right there. So 23, right, yeah. So not all the way to negative infinity. This is one that doesn't extend all the way to negative infinity. But from 23 up to where, Vanessa? There, yeah, perfect. 27.5, yeah, exactly. Okay, up to 27.5. There, concave down. All right. Excellent. Y'all did a really good job of that. Okay. A little bit of hesitancy on the inflection point, but that's normal. Okay, that's really normal. All right. It'll take you a few more homework problems, I think, to get really good at picking out that inflection point. Okay. I think that's our. So that's a whirlwind trip of direction and curvature. Okay. So we didn't have too many examples, but that is going to be covered in the Algebra Review Part 2, okay? So you'll have homework problems about direction and curvature in that assignment that's due Monday. Don't forget that Part 2 is due on Monday, okay? All right. Well, we've got just a few minutes left here, and that's just enough for us to get started with Chapter 2, okay? All right, so finally now we're getting into the calculus part, okay? Although direction and curvature really does play a big role in calculus as well, okay? So we're not just we really are already a little bit into the calculus. But remember, I told you on the syllabus that the study of calculus is the study of change in quantities, okay? And so that's what we're going to finally take up now. How is it that we measure change in quantities, all right? Okay, so we're going to give you here 3 ways, and there may be lots of others, I'm not sure, but these are the 3 ways of standard ways of measuring change in the value of a quantity, okay? And they're really very simple. Okay, and really very simple and straightforward, so this is not rocket science at all. Okay, so if you have a quantity that's fluctuating from one time you measure it to the next time you measure it, okay, right? In other words, the quantity is changing, then you can describe that change in that quantity in several ways. The most basic way, of course, is just by actually computing what the change what the value of the change is in the quantity, okay? And so this way of measuring change is called the net change. But usually we just leave off the word net there and just call it the change, okay? Or sometimes I like to call it the total change, but I think in your homework it's referred to as the net change, okay? So how do you calculate net change? Oh, that's so easy, okay? You just calculate the last measurement of your quantity and then subtract off the first measurement of your quantity, and that gives you the net change, right? Okay? So it's just a subtraction problem, okay? Right? Just look at the quantity the last time you measured it, subtract off the quantity the first time you measured the quantity, and then take last minus first, and that's how much it's changed, okay? So, you know, what could be simpler? That's the most basic way of describing change. But like, you know, many instances in life, the easiest way of measuring an amount is sometimes not the most informative, okay? So another way that we sometimes measure the change in a quantity, okay, that also is useful to us and sometimes more useful to us is by calculating what's known as the percent change, okay? So we're not looking at just the amount that the quantity has changed, but we're going to calculate the percentage that the quantity has changed, okay? So that's called percent change, all right? So how do we calculate percent change? Well, actually percent change is related to change. What you do is you take the change, okay, which is last minus first, correct? Okay, so you take the change, you divide that by the first measurement of the quantity, and then you convert that to a percentage. So you multiply by 100% to convert that to a percentage, right? So, and that gives you not the amount that the quantity has changed, but the percentage amount that the quantity has changed, all right, in the time that you've been measuring it, okay? So that's percent change, all right? And then finally now, important for calculus, more important than change and percent change is what we call the average rate of change, okay? And what average rate of change tells us is, on average, how much the quantity has been changing from one instant to the next, okay? From one instant to the next, right? So on average, how much is it increasing or how much is it decreasing from one instant to another, all right? And again, notice that the average rate of change involves the change. You have to calculate the change, right, which is last minus first. And then to calculate this average, you divide it by the length of the interval over which you're making your observation, okay? All right, so say if you're measuring a quantity for 10 minutes, okay, if you're measuring a quantity for 10 minutes, then you would divide your change by 10, right, okay, to get the average rate of change, okay? Or if you're measuring a quantity for 5 years, you would divide your change by 5 to determine on average how much the quantity is changing each year. All right, those are just the basic definitions, okay, of how we measure change. This is going to be by far the most important to us in calculus, okay? But in other applications, these other ways of measuring change are also really important, okay? In business, percent change is particularly important, okay? Almost all change in business applications is measured as percent change, all right, okay? But in calculus, the average rate of change is what's going to be very useful to us, okay? All right, let's look at an example, and I'm going to take an example from business, okay? This is actually one that was kind of important recently. All right. All right, so this table, what this shows is the fourth quarter, just the fourth quarter revenue. So that is the revenue from October, November, and December, okay? Just the fourth quarter, and that we're calling that Y. For Amazon.com, okay? So a big operation. They have a lot of revenue, okay? They sell a lot of items. Revenue is not profit, by the way, okay? Profit is not revenue. Revenue is just the amount they collect from sales, okay? You have to subtract off the cost to get the profit. This is just revenue, okay? So the amount of revenue that Amazon.com has generated in the fourth quarter, of course, that's a very important quarter for Amazon because that's the Christmas quarter, right? So that's when most of their revenue is generated, okay? And this is fourth quarter revenue for each year since 2007. So notice that 2007, in the fourth quarter of 2007, Amazon sold $5 billion worth of goods. These numbers are measured in billions, okay? Amazon sells a lot, all right? In the fourth quarter of 2008, Amazon sold $6 billion, okay? And all the way up through, here's the last quarter of last year. In 2015, Amazon sold $35 billion worth of goods and services, okay, through their website, all right? So you can see Amazon's revenue is increasing, right? Fourth quarter revenue has been increasing substantially, right, over this time period, okay? All right, so, and, you know, everyone knows that, okay? All right, so first question, what was the change? What was the change over this interval, okay? So what was the change over this interval? And let's interpret that number. The interpretation is pretty easy, okay? But it is important, all right? So it is important. So we do want to put the interpretation down. Okay, so how do we calculate the change? Remember, it's just what? Very easy formula. You can memorize it. What is it? Last minus first, right, okay. So it said over this interval, so I guess they mean over this entire time period that's shown in the table, right? So I guess that's from 2007 to 2015, right? So the last would be 35 and the first would be 5, right? Okay, and so there it is. You just take 35 minus 5, and of course that gives us 30, right? See, that's such a baby problem, right? Okay, that's almost trivial. Okay. Now, what's a little bit not trivial is the interpretation, only because I want you to write it down correctly. Okay, right? Okay. So if you were going to explain to your boss, okay, or your grandmother, okay, let's think of your grandmother actually, who may be your boss for all I know. All right. But if you're going to explain this to your grandmother, what that 30 means, you would say, Grandma, the 30 means what? You know, when you're explaining things to your grandmother, you have to, you know, be very clear, right? Okay. So what would you say there? Yeah, so, you know, you might start by just saying the change in revenue was, or is, I guess it could be, 30 billion. Wrong. Okay, all right. Not quite correct, okay? You got it halfway there, but this is a mistake that people always make, okay, when they're talking to grandma, all right? What you said is right. The change in revenue was definitely 30 billion, but you have to be a little bit more precise, okay? You've got to include the time period, okay? That's very important, because if you just said the change in revenue was $30 billion, that does not give enough context, okay? It was, when was the change in revenue $30 billion? That's really important to us, okay? So you have to include the interval in your explanation, okay? So to make this answer complete, we need to say from 2007 to 2015, the change in the revenue was $30 billion. I'm going to be a real stickler about this, okay, when you're explaining your results, okay? So I like to put that at the first, but since I've already written this down, I'm going to add it at the end, okay? So from 2007 to 2015. That's really important that you indicate the interval of time, because for different intervals of time, the change in revenue will be different, okay, right? It's not that, the revenue is always changing by 30 billion, right? It changed by 30 billion from 2007 to 2015, okay? All right. Now, let's calculate the percent change, because once you've got the change, then the percent change is really easy to calculate, because what do? You just take your change, right, and do what? Remember the formula now? Do I have to scroll back up there? Yeah, last minus first, which is just the change, which we already calculated, right, was 30, right? And you divide it by the first, right, which was 5, and then don't forget you've got to convert that to a percentage, okay? So multiply by 100%. This is going to be a huge percentage, because 600%, yeah, okay? Yeah, see, Amazon has really been growing fast, you see, okay? So they have really had a huge percentage change in the revenue. How do we interpret that now? You interpret it in almost exactly the same way, except you say the percent change, right, okay, in revenue, yeah, was 600%, okay, from, and again, be sure you put the time period there, from 2007 to 2015, all right, okay. So be sure you put the interval over which you're calculating the percent change. And finally now, let's calculate the average rate of change, all right? The average rate of change, okay? So, and once you've calculated the change, then the average rate of change is easy to calculate. Because again, you take the change, which was 30, right? But now instead of dividing by the first value, what do you divide by? Yeah, the change in time, right? The length of the time interval. So from 2007 to 2015, that was how long? That was 8 years, right? Okay. What's 30 divided by 8? Y'all help me there. 3.75. Okay. All right. So we get there 3.75. All right. Now, here is the interpretation, though, of the average rate of change is a little bit harder, okay? So let me show you how to interpret this, okay? So we would say, on average, be sure you throw in the on average, okay? And again, put in your interval. So from 2007 to 2015, okay, the revenue, let's see, that's a positive number, right? Okay, so the revenue increased by, that is dollars, so it's 3.75 billion, and here's the last final part of the interpretation that's really important. Per year, okay, you need to throw in that per year. What the average rate of change is telling you is, on average, just on average, how much has the revenue increased or decreased each time period. Well, here it's gone up by 3.75 billion per year. It didn't go up 3.75 billion each year, though, because you can look at the table and see that. It went up 3.75 billion on average per year. Okay? All right? One thing I got to caution y'all about walking out early, I usually stop class right on time. We're maybe a minute over today. I do not want you to leave early. Okay? All right? Please do not do that. That is not college behavior. Okay? Not college behavior. So you cannot do that. All right? If I'm running over, stop me. All right? But do not walk out early. Okay? All right. See you on Monday. Be sure to do your homework. Yes.
The what's due on Monday is the quiz.